Hello everyone. In this video, we are going to look at frame analysis. What is that? So if one of the conditions that we had in a truss for truss analysis is violated, like for instance, the mass of the members could not be neglected, although remember, if the mass of the members are not neglected, then we can pass half of it to each one of the joints, so that's not the worst thing to be violated. The worst one is basically when the members are pinned not at the end or in the middle, or like in the middle. For instance, here this member GD is really one member, not two. It's not GENED, it's just GD, and we pinned it in the middle E, and something for ABC, the same. It's one member and we pinned it at point B, which is not even in the middle. So in those cases, really, we cannot consider AC or this GD to be a two-force member because we have a pin in the middle with two reactions. In that case, the assumption of two-force member and the fact that at each pin, the only force that is applied is either basically a tensile force or a compressive force, that is not true. So at each pin, we have to consider two reactions, not just one. And so it makes the calculations of the forces in the members a little bit more complicated. So not only we have to consider two reactions at each pin, also as opposed to trusses where whenever we cut any member, the only force we had at that section, as I said, was a tensile force or a compressive force. That's not the case here. So here, if I go and cut this member GD or ABC or this DC, and if you look, member DC, also the force is applied not at the ends, it's also applied somewhere in the middle. So DC is not even a two-force member. The only thing here that can be considered a two-force member is BE. That's the only one, because no load is applied along it and it's only pinned at the two ends. So if the mass of it is not big, the only thing that we can consider two-force member is BE. The rest of them are not. So if I cut a member that is not a two-force member, let's say cut this GD here, then at that intersection, we have an axial force, we have a shear force, and we have a bending moment. So we have three reactions to find, and that makes the stress calculation on that cross-section a little bit more complicated, which we'll see in my solid mechanics playlist. So that's not what I want to do here. This is about the statics right now. By the way, all of the pictures are taken from Bedford and Fowler Engineering Mechanics Statics book. What we want to find are basically the reactions at each one of these pins. That is what we need to do right now. And later, of course, we find all of these internal reactions and we can calculate the stress and so on. So now where would you see frames in real life where those conditions are not satisfied? Of course, you might say something like this, but this is, you don't see that all over the world. But if you look at the simple plier, that is exactly a frame. Why? Because if you look at this member, this one here, clearly, you see, if it's all one member, it is pinned in 2 points that are not the end point of this member here. Look at this member. This member is clearly pinned down in 2 points that are not the end point of it. And the location that this force is applied is also not at the end or at the pin, it's right here. The same thing goes for this member. Look at this. This member is also pinned somewhere not at the end. Okay, or if you look at this member here, this member is also pinned somewhere in the middle. So none of these three members are two-force. The only thing you might say it's a two-force member is this guy. That's the only thing you might say that's a two-force member. So clearly a simple plier is considered like a frame, and you have to analyze it basically based on what we are about to say. So if we look at this example here, the goal is to find the external reactions, and it's pinned at both ends. So at A and G, also there are two reactions. And there are two at B, there are two at E, two at D, and two at C. So if you look at this, Just by looking at this, you clearly see that there are 6 pins, so there are 12 unknown reactions to find. Do we even have enough equation to find 12 unknown reactions? The answer is yes, in this case we do. Well, where do they come from? To do that, we are going to separate each and every one of these members and draw a separate free body diagram for them. So here is that, what you can see here, it's broken down into 4 separate FBDs. This is 1, this is 2, this is 3, this is 4. So these 4 FBDs, each one of them, has 3 equations, some Fx, some Fy, and some moment about the point. So you have 3 equations per FBD, and you have 4 FBDs, so that gives you 12 equations. So you should be able to solve for 12 unknowns. So yes, you can determine everything. Now, if you look at the free body diagram of the entire frame, just taken off of the supports at A and G, this is what you get. This is the FBD of the entire frame just taken off the supports. If you look at it, there are 4 reactions. And I cannot find 4 reactions with 3 equations. So just by looking at the entire FBD, I cannot find all A's and all G's. I can only find 2 of them, and the 2 others I can find a relation between them. Okay, so if you just look at the entire thing, it looks like a statically indeterminate, but if you look at all these individual ones, then you see you are going to have enough equations for enough of unknowns. Okay, so even these external reactions, you are going to be able to find all of them. Now, why don't you go over this individual in the first place? Because if you look at that, it's not always as easy. You might say, how come? Well, look at this FBD, for instance. What does this FBD give you? Nothing. All it gives you is this T on the top and this T on the bottom, and this is that member BE. Remember, the only 2-force member. Because it's a 2-force member, at B and E, I do not need to show 2 reactions. I can only go with 1 reaction because it's a 2-force member. Now, if you look at this, you might say there are 3 equations. Where are they? Well, 2 of the equations are already used to say these 2 are the same. Why? Because here you said already sum Fy equals 0. So if this one is T1 and this is T2, then that means if this is equal to 0, that means T1 equals T2, and let's call both of them T. So when you call both of them T, already one of the equations was used. Then when you take sum of the moment about any of these pinpoints, that is, let's say about E, for instance, equal to 0, that means both of these forces should be on the same line. Which line? The line that connects these 2 points together. Okay? If one of them has a little bit offset, so one of these T's is not on this line, for instance, is on this line, not only it creates a horizontal force that this one doesn't have and cannot cancel, also it creates a moment. And you might say, well, how about this? So I say there is a T here in this direction, and there is a T on that. So basically the equal and opposite of that. And basically that is to say there are 2 components, right? Because there is a horizontal, there is a vertical. Now, could these T's be like this? No, because they create a couple here. And that will make sum of the moment about Z to not be equal to 0. The only scenario for it to be 0 is if you connect E and B together, these T's should be along that line. So you see 2 of the equations already used in the 2-force member thing. Okay, and what about this direction? Can you take anything from sum Fx in this case? No, because none of these forces are in the X. So this FBD literally is not going to give you any equation. So I said 4 times 3, but the matter of fact, it's not 4 times 3. It's 3 times 3. Now, is that really 3 times 3? Let's find out. So instead of just multiplying, let's see how many equations we can get out of each one of them. And how many unknowns do we have? Because right now, this FBD only has 1 unknown. That's T. There's only 1 unknown here and no equation. So 1 unknown, no equation. How about this? This one has 5 unknowns. T is already considered, so T is not another unknown. So this guy has 4 unknowns. How many equations do you have? Well, some fx, some fy, and some moment. So it has 3 equations. That's good. Now, if you look at this one is similar. T is already taken care of. So you have the 2 G's and the 2 D's, and G and D are different from A and C. So again, this one has 4 unknowns. And it has dimensions and everything. So it has 3 equations. And when you come and look at this one has no new unknown. Why? Because the C's of it are considered in the other one. The D's of it are considered in this one. So this one has no new unknown. This one does not have any new unknown. But this one can give you 3 equations. So how many total unknowns do you have? You have 9. You see, there is 4, and there is 1. There are 9 unknowns. How many equations? 9. 3, 3, 3. So that is really not 12 equations, 12 unknowns. It's 9 equations and 9 unknowns. Okay? And you can do that. So you don't need this middle one. You might say, does this middle one give me another one, which is the same as this top guy here? Looking at the entire FBD, no. If you use the individual ones, then this top one only gives you equations that are a linear combination of previous equations. So this one is not going to give you anything extra. Or if you use that, then the other ones are not going to give you anything extra. Okay, so it's up to you whether you want to go just with these individual ones or go with this big one. The good thing with this big one is it can give you some of the unknowns directly with 1 equation and 1 unknown. The problem is, if you look at here, if I sum of the forces in the x direction, then what would you get? You get Cx in it and Ax. You get 1 equation and 2 unknowns in it, which is not solvable. If you do sum Fy, then you have 3 unknowns in it, again, not solvable. If you take sum of the moment about any of these pinpoints, again, there are 2 unknowns in it. So although you have 3 equations, but since you have 4 unknowns, from none of these equations, you can find any of these unknowns directly. So no direct number comes from any of the, calculated for any of the unknowns in this top FBD. If you look at this one, there is a similar scenario. Okay, take moment about C or D. There are 2 unknowns. Take sum Fx, take sum Fy. There are 2 unknowns. And exactly similar to this. So if you use any of these equations, there will be no single equation that has only 1 unknown in it. All of them have more than 1 unknown, so you have to solve all of them at the same time. And you cannot do elimination or anything. You have to write it in a matrix format and solve it. But if you look at the big guy here, there are equations that can help you. You might say, which one? If I use some of the fx here, well, there will be 2 unknowns in it. So that is not going to help. I want 1 equation with 1 unknown. So if you use some fy, again, there are 2 unknowns in it. So that's not useful. But can I use the moment equation? Can I take some of the moment about 1 point? Which point? This point. Or this point. The point that has maximum unknowns on them. So if I take some of the moment about g, that can help. Why? Because not only gx and gy will pass through g, also ay is passing through g. So the only unknown force that creates moment for g is ax, so I can directly find ax. As simple as that. You see how good it is? So what forces are creating moment about g? Ax does, and it's clockwise, and the distance is 2, so it's going to be negative 2 times ax. The 6 does, that is also clockwise, and the distance for it is 3, so negative 6 times 3. And this 8, this is also clockwise, so this is going to be negative 8, and the distance for it is 1 meter. This is equal to 0. And if you solve for ax from here, you are going to get negative 13. kilonewton. You see, I found one of the unknowns with only one equation. Now, if I say sum of the forces in the x direction, that is going to be what? That is going to be ax plus gx plus 8. This is equal to 0. A is already calculated. From here, you can directly find gx. And gx is going to be 5 kilonewton. You see, so I could find two of these unknowns directly, one equation, one unknown. That's perfect. So I got two of them done. Now you might say, can I find ay and gy similarly? No. Why? Because if I take moment about a or g, now g is already used. If I take some moment about a, that will give me gx, which I already found. If I take moment about any other point, let's say b, e, c, or d, both ay and gy will appear in all of them. And if I use some of the forces in the y direction, again, both ay and gy will appear in them. So there is no single equation that gives me one of these. And here is the place that you might go wrong. You might say, what if I do sum of the fy equals 0? That gives me one equation between ay and gy. And then maybe sum of the moment about b or c equals 0. That gives me another equation between ay and gy. And then I solve a 2 and 2. Two equations, two unknowns. The answer is no, it doesn't. These two equations will be the same. They are exactly going to be the same equation. Don't be tricked to assume that you can have 4 equations of equilibrium. You already used 2 of them. So you can only pick one of these. The next one is not going to give you a new equation. And if you don't believe me, just expand it, see what you get. So sum fy is going to be what? It's going to be ay plus gy, right? And then what? Minus 6. That's this equation, correct? Now let's take some moment about c or any other point. It doesn't matter. You know, let's just use maybe, I mean, c is good, but c removes ax in it. That's fine. Let's just use c. So what would you get here? Ax passes through it, so nothing. Ay does a clockwise, so it's going to be negative ay times 3. That's for ay. This 6 doesn't do anything. That 8 is a counterclockwise times 1. Gx is counterclockwise times 2. And gy is clockwise times 3. This is equal to 0. Yep. Now, how much is gx? Let's plug it in. Gx is 5. So I'm going to plug in a 5 here. So that is 10. 10 plus 8 is what? 18, correct? So this total number is 18. Now go ahead and divide this entire equation by a negative 3. Divided by negative 3. What would you get? That becomes ay. This guy becomes gy. And positive 18 divided by negative 3, that's negative 6. Look. That's the same as this one. So you can only get one equation, not 2. You can use any of them, but don't write it twice. Okay, that's the best that you can get. Ay plus gy equals 6. So I call this equation 1. I'm going to use equation 1, and I found 2 of my unknowns. Good. So now let's go and solve the rest of them here. Okay. So pay attention that I have ax here and gx. Wherever I see ax and gx, you know I have them. I have a number for them. So this is negative 13. This one is 5. Correct? And I assume that's it. Remember, we are not using this anymore. We already used it. And this one, again, remember, that doesn't give me anything, so no time to waste on it. So now I only have to focus on these 3. This is all I have. These are my 3 FBDs, and they should ideally give me all that I need. Now, which one would you attack first? And there is one extra equation that I had, and if you remember, it was AY plus GY minus 6 equals 0. Remember, I also have this equation from the big FBD. So now, which one of them would you get first? You ideally want to go after one that's with one equation you can get to solve for one unknown directly. Is there such a thing? Well, if I come here, remember, the x equation in this one could directly give me cx because there is only ax and cx, no y. So in this one, I'm going to use some fx, which is ax plus cx, right? Sorry. Equals 0, but ax is already negative 13, so cx is going to be positive 13. Similarly, in this bottom one, I can do a similar thing. I can do some fx on this one, and that is going to be gx plus dx equals 0. And gx is 5, so dx is going to be negative 5 kilonewton. So here I got 2 more unknowns down. So I got this one taken care of, and this one. Okay, now what? Now, if you look at this guy here in the middle, which has only 4 unknowns, these other ones have 5 unknowns, top one and bottom one. This one has 4 unknowns, so this is a better point of focus. And already 2 of the unknowns are taken care of, so it only has 2 more unknowns to go. And guess what? I have not used any equation here, so it's time to do it. So here, I go ahead and take some of the moment about C in this one. Why? Because it takes away the cy that I don't know. The only thing remaining is dy and the other known values. So there is 8, and it's clockwise, so it's going to be 8 times. And remember, this distance was 1. And then what? You have a dx, which is clockwise. And the distance for dx was 2. And dy is also counterclockwise. And the distance for dy is this guy, which is, if you look at it, so that is a 3 and 1, 1, 1. So it's this guy, 1. So that is a 1. This is equal to 0. And remember, dx, I have it. dx is negative 5. So this guy is negative 5. That should allow me to directly calculate dy here. And that makes it negative 18 kilonewton. And then I use some forces in the y direction. Why? Because the only forces are cy and dy. And since dy is already calculated, I can see cy is positive 18 kilonewton. There we go. So I got cy and dy taken care of as well. I go back to the big picture. Wherever I have cy and dy, I mark them down as known. So now I have this one, and I have this one. Okay, so there are only, as you can see, 3 more unknowns to go, ay, gy, and t. That's all it is. So for instance, I can come in this one and take some of the moment about g. Yg, because gy goes away, only t stays, and dy. So that is going to be t times the distance, which is 1, and plus dy times the distance, which is 2. Nothing else. That is equal to 0. So clearly t is going to be negative 2 dy. That is 18. So that is going to be positive 36 kilonewton. So you found the force in this two-force member. So T is taken care of, and this T is taken care of. And so now in here, you can simply use sum Fy equals 0. And there is Ay and Cy and minus T and minus 6 is 0, but guess everything else is known except for Ay. Because Cy is positive 18, and this guy is positive 36. Okay, so that's negative 42, 18, negative 24, so I get positive 24 kilonewton. This is one of those external reactions that you could not find here. Remember, Ay you could not find. Now you do. And now if you want, you can go back and use this green equation that you had already. So you can combine these two together, or you can go after one place that has G in it, which is like this. And in this one, if you want, you can use sum Fy equals 0, and that should give you Gy. Or again, as I said, you can plug it, this number here. You can go ahead and plug this number right into this equation, and that should give you what? That should give you Gy. So here, this is 24, and minus 6, that's 18. Take it to the other side, you get negative 18. So Gy should be negative 18 kilonewton. Done. Now if you look, I have all of 3 here, 5, 6, 7, 8, 9, 10. Okay, right? So I got 10 unknowns. And was it everything that I had? Well, in this case, yes, it is. Because remember, this guy only had a T in it. And there were basically some extra here, here, here. So 10 equations and 10 unknowns is what you had, and you could solve for all of them. Okay? Now, if somebody says, what's the reaction in some member if you cut it? How much is that? Well, it depends on the member. So if I cut member BE anywhere, right? So if I cut member BE, let's say I cut it somewhere in the middle. So this is point B. And here I have T. And remember, T was 36 kilonewton positive, which means the member is under tension. What reactions do you have here? Well, clearly it's a two-force member, so clearly this is just going to be a 36 kilonewton force. Or you call it T or V, doesn't matter. That's all it is. But if you look at another member, let's say, for instance, member ABC. If you look at ABC, let me show you ABC first. So this is ABC, and at A, what do we have? We have AX and AY. AX was negative 13, AY was 24. So this is negative 13, this is 24 at A. Then we have B, and then we have C. At C we had CX and CY, 13 and 18. So this is 13, this is 18. And at B, we had basically only the T downward, and the T downward was 36. So this is this member, okay? First of all, is this member at equilibrium? Yes, because this is negative 13, that's positive 13, sum fx is 0, sum fy, if you look at it. Now, seems like we made a mistake somewhere. Did we know? Actually, I forgot to add one thing. I forgot to add this 6 kilonewton. You have to add that here. So if I go back there, there should be an extra 6 kilonewton right here. So if you look, 18 and 24, 42 upward, 6 plus 36, 42 downward. That is 0. And if you take sum of the moment about any point, that should also be 0, right? So you can just check one of them. Let's take it about C. So about C, this 24 and this 36 should cancel each other. And this 24 is multiplied by distance 3. This distance is 3. And this distance is 2. So 2 times 36 is the same as 3 times 24, 72. So you see that sum of the moment is 0. So clearly this member is at equilibrium perfectly, and we did not make any mistake. Now if I go ahead and cut this here, now clearly if I cut it there at this intersection, there should be a P force to cancel that 13. So this 13 is this way, so that P should be a 13 this way. There should be a V force to cancel the two of these, right? Because the FBD of the left section here is going to be like that. So you have a 36 here. There is a 13 this way. Let me change the negative and make it positive, but turn the direction of it. This is a 24. So remember, I said there should be a 13 here. And this force should balance between these two, 36, 12, 24, so there should be a 12 up. And there should be a moment here. So sum of the moment about this point is 0, because clearly these two won't cancel anymore. And that moment, whatever it is, depends on how long in this distance we cut. What is this distance? Based on that, we can determine the moment, which I did it in my solid mechanics lectures. It's called shear force and bending moment diagrams, and I have done that. Okay, so clearly at any section there is more than one axial force. There is a shear force and there is a bending moment. So this is frame analysis, and that's just because the two force member assumption is violated. Hopefully the video was useful to you. I'll see you in the next lecture. Thank you.